Welcome to the storage systems course. This is being offered through NPTEL, and my name is Gopinath. I am from Indian Institute of Science, where I am a professor. Okay, today let me briefly mention what storage systems is all about. I think most of us have used computing systems, and our computing systems usually store some information and we try to retrieve it later. Some of it directly what we store and retrieve, some of it done by other parties. For example, if you write a mail or if you write some document, you create it and you retrieve it. Sometimes other people are doing it for you. For example, if you use a Google file system or a Google system for searching, somebody is storing the information and you are using them indirectly. Okay. So, storage systems can be small like the ones which we create ourselves, or it can be very big like the ones which Google and Facebook, those kind of parties provide or create. Now, the important thing for us is to know why storage systems have become important. In the past, typically we find that the processing and storage used to be together. Even now, if you look at a current PC, you will find that the storage comes with the PC, right? The storage is not outside the PC, it is always inside the PC. So, and also it sits on a particular bus, and what is called a PCI bus, okay, which is electrical bus. Okay, so that means that it has to be present close to the CPU, okay, because it's sitting on a bus. It is not on a network, okay. The storage is not a network, it's actually on the electrically connected to the CPU, where the CPU is connected. Now, so in the past, it always has been the case that storage was an integral part of the computing systems, and also that's the reason why even the operating system would consider storage as its an important component. Because an operating system also cannot boot without its kernel image, etc. available on storage system. Okay. It was an integral part. So, it was quite natural that processing and storage were considered together. But with fast networks, this has changed. So, because of that, nowadays you will find that people often say that there is processing, storage and networking. Okay. And some of you might already have experience of this. In local area networks, you will find that your directories may be accessed through networks. For example, there is a protocol called NFS, Network File Storage, which you don't have the storage on your machine on which you are working on. It's actually being provided to somebody else, some other machine. So, there's something called network storage that's available to you. Okay. So, essentially the processing is happening on your local PC, your storage is coming from what are called NFS servers, and they are connected through networking. And this is feasible because fast networks are available now. For example, in 1980s you had 10 megabit per second Ethernet, early 1990s you had something called fast Ethernet, about 100 megabit per second. And about 2000s, we had something called gigabit Ethernet, which is 1000 megabit per second. And in the near immediate future, you are getting 10 gigabit per second also. Okay. Once you have fast storage, it turns out accessing data or storing data is not going to be that costly of an affair. It can be done fairly efficiently, okay, in small amount of time. That's why what has happened is that these networks have enabled separation from processing. Okay. So, that is basically the critical issue. Okay. So, if you separate them out, then the accessing party and the access party, okay, that is the client and the server, they have to understand how to make sense of each other, right. One guy is requesting, one guy is responding. That means that there has to be some kind of a protocol in place. Okay. So, in addition to protocols, you also need certain way of managing the systems, okay, the two combined system, because there is a client here, there is a server here, and there is a network here, right, in between. Now, anything can happen to any of these three things. The server can die, the client can die, the network can die. Somebody has to manage it. So, there is now a system also required, okay. So, in the previous systems, you definitely had devices, okay, disk etc. were there before networking, they are going to be there afterwards also, okay. So, you will have the same devices as before, but now we are going to have a protocol, because you have client and servers which need to talk. If they have to talk, they need to have a common way of understanding each other. That is the protocol. And you need some management in addition, so that you have multiplicity of actors, things like client, servers and networks. You need to figure out what they have to do, how they have to be started in the beginning, how, if something fails, how we have to handle them, okay. So, I have given some examples of this. If you look at devices, you will have things like tape, drum, disk, and nowadays solid state disks, okay. Drum etc. is obsolete, tape is still going on for very high density storage and low cost, this is still good. Disk is widely used, it's been used for the last 50 plus years, but I think there is now a significant threat from solid state devices, okay. Now, there are a lot of protocols. I mentioned already a networked file storage, there is NFS. In the Windows world, there is something called CIFS, CIFS, and nowadays, because there is what is called cloud computing systems, you also have what is called cloud storage. For example, when you use your Gmail system, your Gmail client on your system, right, on your browser, right, it's actually accessing your mail using some API, okay, which Google has provided, okay. Similarly, if you are talking about Facebook etc., there is some API by which you are accessing some of the data, okay. In the case of systems, we can think about, let us take mail storage. Now, there are some protocols, you might have heard about something called POP3, IMAP4 etc., okay. So, there are, the mail is stored, each piece of mail is stored as a possibly separate file. You need to be able to tell it which file you are talking about, which file to delete, which mail to retrieve etc. All those things are basically, the IMAP essentially gives you some let us say a protocol by which at application level, now this is happening at application level, because this IMAP is being used by your mail client. There is one more level below, which is the storage client aspect, okay, the storage server side, okay. There is one more level below that, okay. But from our point of view, we can club both these things together and say that at an abstract level, from the point of systems, you are basically using IMAP or POP3 as a protocol to name pieces of mail, read the mail or delete mail etc., or move things around, okay. All those things are able to do, okay. Now, if you look at the issues that were there in the previous systems and the current systems, you will see some small changes in some areas and some major changes in some other areas. If you look at what was the issue with old systems, old storage systems, the most important issue was concurrency with CPU. Why is it an important issue? Because notice that the throughput of a system depends on how quickly you are able to access the storage blocks. Good example is consider booting of a system. When you are booting the system, you are going to pick up the kernel or the operating system parts of it from the storage system, okay. Now, how quickly you boot depends on the speed at which you are picking it up. Now, while the system is booting, it can be doing other things, it is initializing certain things, right. So, while initializing is going on, you can in principle access other blocks required, other storage blocks. So, while the booting is going on, two things can be going on. One is initializing of the operating system structures, as well as picking up what is might be needed in the future, okay, those blocks, storage blocks. So if you are able to keep both these things going at the same time, you will have higher, let us say, throughput, or you will get lower latencies with respect to your booting, etc. You can also use the same model for applications also. Applications, what happens is that you could be doing some computation, and then you can also be once in a while accessing the storage devices, and storage devices are very slow. Okay, they are about 4 orders of magnitude slower typically. Okay. So that means that you have to find a way in which you can keep the CPU going at the same time as the storage systems also. Okay. So that's why concurrency is an important issue. This is also an important issue even now. This has not gone away. Okay. Similarly, if you look at device diversity, what is device diversity? As I mentioned earlier, we had things called drums, we had something called tape, disk, solid state, etc. And there are varieties of them. Okay. There is not one single variety of disks, there are actually multiple generations of disks. Okay. For example, you might have something called IDE disks, you might have something called SCSI disks, you might have something called, nowadays you have something called SAS disk, now we have something called solid state disks. Okay. Varieties of disks are possible. So the thing is, you need to be able to handle the diversity. And again, these things are very core components of operating system design. How to keep systems concurrent so that multiple activities are going on at the same time. How to handle varieties of things, because the operating system is changing all the time with types of devices. Newer devices keep coming in. You have to figure out how to keep the operating system structure stable while devices are changing. Okay. For example, if you look at it, a Linux kernel does not change because a new device is coming. Okay. You just write what is called a device driver, which helps it to access that device. Okay. The structure of the kernel itself is still about approximately mostly the same. Okay. The core kernel doesn't change that much. The way it is done by is using some things called device drivers, and that is one way to handle device diversity. And that is the same thing even with the case of even current situation. So this has nothing has changed here. What is the new thing that are changed in the storage systems? One is scale. In the past, for example, when I first started working in this institute, for example, my disk was 5 megabytes. Okay. Later it became 40 megabytes. Okay. Now I have a 250 gigabyte disk. Okay. And my students now have a 3 terabyte disk. I still am with the 250 gigabytes. Okay. And Google is about hundreds of petabytes or more. Okay. So the scale has become dramatic. Okay. It is distributed also. It's not in one single place. Nowadays you will see that I have some stuff on my memory stick here, I have something on this system here, I have something at my laptop, I have something on my Gmail somewhere. It's distributed all over the place. That is from personal point of view. But if you are talking about a big company or organization, their data also is distributed. For example, if you take Indian Institute of Science, there are lots of departments, lots of administrative documents which are scattered all over the place, right? So the storage system that is handling this will also be at multiple places. Okay. This other thing that you have to worry about is error management. Why is this an important issue? Because once you have large amounts of data, you will find that there can be multiple ways in which the data can become bad. One is that a lot of people are using it. So you are, in spite of the best training, people sometimes get things wrong. They delete files wrongly, right? It must happen to you. It happens in organizations also. Okay. So that can be problematic. It could also be because of the hardware itself going bad. Okay. A good example is, some of you might have experience of having CDs which are no longer readable. In the past, for example, earlier 20 years back, we used to work with floppy disks, and we used to always worry that the floppy disk will go bad. And this is basically multiple reasons by which can happen. You can keep it on a hot sunny day, keep the floppy somewhere else, it will bend in some ways and you might find that you're no longer able to read it, right. The reason why CDs fall apart is because they use certain dyes and the dyes can go bad, organic dyes they use which can go bad, okay. Even discs can go bad because it turns out discs have sectors and they use some fairly sophisticated means of error management, what are called error correcting codes. But in spite of error correcting codes, sometimes you find that certain errors cannot be corrected, okay, and the sector goes bad, okay. When the sector goes bad, then you lost the data, okay. So, why the sector goes bad? There are a lot of reasons for it. We will not go into it, but the reality is that sectors do go bad and you have to work out the things. Actually, it turns out even when you build the disk itself, certain sectors are bad in the beginning itself, okay. And there is some mechanism already present on the disk which basically does what is called something called error lists, bad sector lists, and you map those bad sectors to spare sectors sitting outside somewhere at the edge of the disk, okay. So, all those things are already present in disks, okay. You will find that any big system, any large scale system, like for example, take any 3 terabyte disk or any solid state disk which is coming out, they have a lot of capacity for handling this kind of errors, okay. It is part of that device. But in addition to local disk level error management, you need to have ability to handle errors that span multiple devices. For example, you might have a file which is, let us say, cannot fit into one device. That file is going to be split into multiple parts. One of the parts of that one part of that device can fall apart. That means your file no longer may not be available in one, let us say, complete whole. So, you will have to find ways to get around that problem. Similarly, security, right. I think people store varieties of data, some are publicly readable, nobody cares, but some are sensitive, you want to make sure that only certain people can see it. For example, most of us have some passwords or whatever or pin codes for accessing sensitive information. You might write it down somewhere, I do not want anybody to see it, right. Even if you look at, for example, SSH, those of you who used SSH, there is something called a private key and a public key. The private key has to be kept secret from everybody other than yourself. Only you should know it. If somebody has figured out your private key, what can he do? He can forward the message as if it is coming from you, okay, and send it somewhere. Another person will believe that it has been sent by that party only, not the person who has stolen the private key, right. The private key has to be kept secret, okay. And there is some security model that has to be available so that the private key remains secret. How is it done in Unix systems? It is done by using, it has got something called permissions, right. Those of you might have looked at it, there is something called read write permissions, right, and Unix system has was originally devised, this permission system was devised in the mid 1960s, and basically they thought of it as the following: user has read or write permissions, then there is something called a group, and group parties can have read and write permissions, and then this other, anybody outside, okay. And that model is quite good, but the other people have also improved on it. There is something called access control list, which is there in, for example, more recent operating systems, and that also gives security of a particular kind, okay. There are other types of security that can be thought about. If access control is not applicable, then it turns out that you might need to use other mechanisms, for example, cryptography. In the case of the earlier model, I was talking about the permissions model. Every access you make of the file is mediated by the operating system, right, or the file system. But suppose the data is not present in one system. It moves across from one system to another system, right? There's no one single guy who's able to ensure that it remains secure as per the policy. It's not one single person, right? That means that intermediate parties multiple parties can be there, right? For example, I am trying to access my bank account, right? I have my PC, there is a server that side, there are various intermediary devices, right? I have to make sure that there is security at each level, right? So I might need to use access control will not work seriously here. There are models for that also, but typically cryptography is used here, okay, because there's not one single person who is watching all the sections from one side to other side, end to end, okay. So same thing with storage systems. If you have a large scale storage system, you might have to use both access control models. Also, you might want to use cryptographic models, multiple security mechanisms, so that the security policy at high level, what has to be observed, can be provided, okay. Now, there are also systems which want to guarantee storage systems. You need to provide real time, let us say, real time operation. What it means is that suppose you are using video, you want to make sure that your data comes in within the required latencies. If it doesn't come in, then your video becomes not so interesting to watch. Audio is, for example, much more stringent compared to video. So there is something called hard real time and soft real time. So you can be listening to music and you want to make sure that the data is picked up and given to you, to your application, the music player, in the right amount of time, okay. So your storage system also has to do it, okay. So there is a networking aspect, the application trying to read the music file and play it for you. So there is a real-time aspect relating to the application, real-time aspect relating to the networks, there is a real-time aspect relating to storage also. Okay. All three have to be together, then only there is some reasonable experience, okay. Oftentimes it is very difficult. So what people do is, they try to engineer a system sufficiently well, that in spite of not being able to manage the real-time aspect in each of the three places, they still can give you some reasonable performance. That is, you make sure that it is the latencies are small enough that only if they grow by a large amount, then you see the problematic aspects, okay. So similar to that, real time is the quality of service, and these things are becoming important, but storage systems still are not, current storage systems are not very well geared for these issues. These two issues are not very well geared for it. A good example of why these are important in the future, some of you might have heard about something called Netflix. What is Netflix? It's a big video it's a distribution consumer system, right? Basically, you can watch movies and they have all the videos, right, on some servers, and they're going to stream it to you, okay. So now your experience of watching that movie, and typically these are all high definition, etc. That means they are much higher quality than let us say what has been so far, right? And that means that the storage required to store them is also very huge. They are not small files, okay. They can be in the region of tens of gigabytes, okay, and there has to be continuously streamed. And what is more important is that the streaming is happening on a wide area network. For example, the Netflix servers could be sitting in one city and I could be watching in some other place. That means I have to guarantee that in spite of whatever networking elements that come in between, whatever software processing elements that can come in, whatever storage elements that come in, they all have to somehow deliver these packets needed for display at the consumer side, right, at reasonably good rate, so that the requirement for good video display on the consumer side is not affected, okay. So that's a fairly complicated thing. So you have to engineer some of the systems extremely well, and also other more important problem is that the scale also is important. You look at Netflix, right? Some of you might have heard that now Netflix is about supposedly 30% of all internet traffic, okay, 30% of all internet traffic. That means it's really become extremely big, okay? Even web is not as big as Netflix, okay. You thought web is big, right? We all, so many of us use it, but web is nowhere, let us say, as big as Netflix, I'm told. Okay, I'm sorry, I made a mistake. I should say it more correctly. Netflix is 30% of the web traffic. Sorry, that's the right word to say it. Okay. The other issue is manageability. Okay, what I mean by manageability is that when you have so many things around, how do you ensure that things, when they fall apart or they're not working well, there's somebody watching it and trying to correct it. Okay, this turns out to be a fairly tricky business. Okay, so for example, we talked about error management, right? So it may be that one copy of you, to make sure that you don't lose anything, you keep multiple copies of a particular piece of information. If one of the copies becomes bad or is lost, right, you will have to use the alternate ones. So somebody has to figure out where to pick it up from and ensure that that copy is available. Okay, so that is one aspect of it. The other aspect of manageability could be performance. Okay, I say that I have a video thing to be shown, I want a particular guarantees. Okay, somebody down the line has to ensure that this is given to you. Okay, somebody has to manage it. So there could be lots of types of accesses. Somebody might be web traffic who doesn't care that much about real-time aspect. People do worry about quickness, but they may not be saying that I have to have it within, let us say, 100 milliseconds. Okay, they might be happy if it comes within 50 milliseconds or 100 milliseconds or 400 milliseconds. I don't notice a difference. If it comes in 10 seconds, I worry about it. Whereas in the case of video, I have to ensure that I get a frame every 1/30th of a second. I need to get one full frame. Okay, that whatever stuff is there, right? I need to get that about every 30 milliseconds. I need to get one frame. Okay, if I get it much larger than that, for example, 100 milliseconds or 500 milliseconds, then that frame cannot be used. Okay, so somebody has to manage the systems so that whatever objectives were there with respect to the service are being handled. Okay, so storage systems also have big issues of this kind. Okay, now let's just quickly look at why storage is different. Now let's take this to, you may be aware of many aspects to it, but let me post you one or two things you may not have thought about. There is the issue of what is called long-term storage. What is long-term storage? I want to store something for multiple decades. Why is this important? Somebody writes a book. Nowadays, most books are being written digitally, right? And I want to access it about 10 years later, 20 years later, 40 years later. Now, with books, the physically printed books, we take it for granted. For storage, it's still an unsolved problem. I'll give you my own example. I did my PhD. I wrote my PhD thesis in 1988. It's written, I'm not able to, because it uses some old form of PostScript. I cannot print that PostScript file except on a particular printer that was available in 1988. Okay. Luckily, I don't depend on that particular thesis. Actually, I wrote a paper to another conference, and that is the only thing I can give it to you. Okay, I cannot give you my thesis. Okay, whereas some other parties might have even wrote it. At least I wrote it in PostScript, old version of PostScript. In the 1980s, early 1980s, there used to be lots of other, let us say, editors available. WordPerfect, Star, etc. Okay, and it's not easy to get hold of machines which run that software now. Okay. So if you wrote your thesis using Star or whatever it was, it's going to be a lot of difficulty for you to access them now. Okay. It can be done. One way to do it is doing what's called, you can virtualize that application, okay, and run it on a virtual machine using the infrastructure it needed to run Star or WordPerfect in those days, and run it as a virtual machine on your laptop, current laptop. It's possible, okay, but it requires that somebody has done all that work about how to have a virtual machine which is able to run that operating system of that time, okay, and with all the devices of that time. For example, those days you had 8-inch floppies. Suppose you had your thesis was on an 8-inch floppy, okay, that's all you have. I want to see it on my laptop, current laptop, okay. You can think of it, it's not trivial, okay. Basically, first of all, I need to find a physical device which can take that 8-inch floppy and be able to read the bits out, okay. Once I get the bits out, then it has to be processed by the various software which understands the blocking, the way in which the blocks on the or the sectors on the floppy device, right, they all have to be readable, right. They have to be partitioned, they have to be cut into those pieces and then provided to the current systems, okay. Then only they can actually make sense of those things, okay. So, basically our formats, devices, etc. can change, okay. And what is most interesting is the data is not interpretable unless auxiliary information also stored, okay. Now, this is very interesting issue here. Why is this interesting? Let us think about, I think I will try to illustrate this, okay. See, in the past, for example, you might have some character set, that's something called, let us call it EB's EBCDIC, EB's EBCDIC. These are old IBM format. I shouldn't say old because there are mainframes which still use this, okay. So, I might have my, this is just like ASCII, this also is an 8-bit code, okay. Suppose I have written a document in EBCDIC, okay, then somebody has to translate from EBCDIC to ASCII, somebody has to do it, okay. Now, it's not as simple as that, because it turns out if you look at EBCDIC etc., there are various ways of saying stop, because once upon a time these characters things were being sent on certain telecommunication media. So, they used certain codes for saying stop the transmission, restart the transmission, okay, etc. Okay. Even ASCII has got this. Okay. For example, in ASCII you have something called control S. What is control S? Means stop the transmission. Control key means what? Continue the transmission. Okay. So, there are various characters which have different meanings across this. Somebody has to interpret these things and map it to the new meanings or try to emulate them in some way, so that whatever intent that was there here should be captured here, okay. So, this is basically what is called emulation, you need to emulate it, okay. Now, this can be simple sometimes, it can be quite complex sometimes, okay. And the easiest thing to do it is to use virtual machines, but even then the complete environment has to be preserved. Why is that? Because let us take the case of PostScript, right. Now, what is a PostScript? PostScript is a document formatting language, and this PostScript, okay, has certain ideas about fonts, it has certain ideas about how to, let us say, rotate something, okay, because you can write some primitives in this system by which you can rotate an object, etc. Okay. Now, it can also have certain models like color, okay. For example, it might say show me certain types of color, okay, because even the color is encoded. Some of them might have 256 colors, some of them have million colors, etc. Right. All those things are possibly encoded here, okay. Now, that means that somebody some hundreds of years from now, okay, should know that PostScript has a certain model of the document, okay. They should know, okay, that there is some concept of color, that it's a 2-dimensional surface, it's not a 3-dimensional surface, it's not a rich n-dimensional thing, right. Or even simple things like, if you take a book, it has got something called content section, it has got something called index section, it has got some chapters, etc., right? There is some structure to it. And each of the documents will have some information about that, okay? So, that what I would call as a metadata for the book. Similarly, any document, if you take any PostScript document, a PDF document or a doc document, it has a notion of some structure, and that structure depends on how you interpret the document. That means the software at that time has that information in its mind because the code is written that way, and it knows where to look for, where the index is, where the bibliography is, where the contents are, etc. It knows that where to look for, okay. So, it can go ahead. But suppose I go to a new model altogether, right. I need to have the information saying that this particular document has the index at this place, has the contents here, etc., right. That information also has to be transferred, otherwise I can't make sense of it. That means that there is some metadata about the document that has to also be transferred across. Then only anybody who is looking at that can actually make sense of it. If that metadata is not available, then I can't figure out what's going on, right. So, in a sense, what's going to happen is that suppose you just think that there is a floppy, it has got, everybody knows that what we store in a floppy is zeros and ones. So, somebody, some clever physicist around, he takes an 8-inch floppy, he is able to shine a laser or whatever on the thing, he is able to see zeros and ones. So, you get a string of zeros and ones, right. But what can you make of it? Can you make anything out of this zeros and ones? Because you need to know the structure of what was stored there in those days, right. For example, you may have what is called a master boot record, which is sitting in some place. You need to know that, okay. There is some master boot record sitting at the beginning, the first sector might have that information, okay. But you also need to know how big it is. Nowadays we don't know, nowadays we think it's all 512 bytes, etc. Who knows? It may be 512 bytes then that time also, the floppy. But one can think of it that it could have been 256 bytes. There is no reason why it has to be 512 bytes. Actually, nowadays you will see that disks are going to, from 512 byte sectors, they are trying to go to what is called 4K sectors, that is 4000 byte sectors. Okay, it has not happened completely. People are beginning to do it. For efficiency reasons and other reasons, people are going towards that, okay. That means that once upon a time it was more or less clear that any disk we had, the sector size was 512 bytes, okay. But in the future, just about 5, 6, 10 years from now, probably most of the disks that you will see will be 4K byte, okay. So, there is nothing which says that in the future, 100 years from now, that also will not change. That means that there is some information about the sector size that is critical. Without that, you can't make sense of whatever rest is coming, okay. So, in a sense, what is happening is that if you want to understand a document, it has some suppositions about how to interpret the document. That information also has to travel across, which becomes very difficult, okay. So, that is what I was referring to, okay. Data is not interpretable unless auxiliary information also stored. What is auxiliary information? Things like sector size, etc., okay. It is not obviously, the disk is there, I can see the disk, I can see the floppy, it's all, I know it's all 1 0 zeros, but I can't make out sense of it until I know what sector size it is, or for that matter whether it is used compression. If it is used compression, I need to know what method of compression was used. If it was encrypted, I need to know what its secret key was, okay. You don't tell me any of these things, I can see zeros and ones, but that doesn't help me, because I can't decrypt it, I can't see, uncompress it, I can't do any of these things. So, what is the real problem right now is that along with data, I also need to store auxiliary information. Now, the auxiliary information also has to be stored, okay. Where is that? Who is going to store it? Okay, because my problem is to store the data, but now I have got a compounded problem of storing auxiliary data also. That also I have not solved, because it also has to travel across time. About 100 years from now, both has to be there. So, it turns out to be a very difficult, tricky problem. Nobody has solved it. So, the only solution is to keep changing from current format to future formats every so often. Keep changing it. Keep following the technology cycles. You had 8-inch floppy, then take your data and put it into 3.5 inch floppies, then put onto CDs, put onto DVDs, put onto Blu-rays, put onto holograms, I don't know, whatever, okay, put onto that, put onto this, keep on, you have to do it, okay. If you don't do it, your data will be lost, because one day that gadget that reads it may be lost, okay. Of course, you always have a solution, because finally the bits are physical, zeros and ones somewhere, right. So somebody can, from using physics, they can do it, okay. They can look at the bit patterns, they can see, use some laser or whatever light they can use, they can see zeros and ones. But that doesn't solve the problem, that you have to remember, okay. The fact that I can see zeros and ones not solving the problem. Why? Because I cannot interpret the zeros and ones. If you give me 1 million bits, zeros and ones, I can't still say what it is. Somebody has to tell me that the first few bits are this, next few bits are this, okay. Somebody has to tell you all these things. That also is some kind of information, the metadata, okay. Unless you also make that happen, okay, you cannot really do that, okay. That's why it is a very hard problem, it's not a trivial problem, okay. Similarly, if you look at security, you will find that storage security is quite different from network security. Some of you might have heard about saying that you can use cryptography, etc., right. It's true, you can use cryptography, but it turns out cryptography is just a single mechanism, it's not really solving the whole problem, okay. I think I already mentioned to you that if you are using SSH, you have to store the private key somewhere securely, okay. For cryptography, you need this private key and public key. Now, if you tell me that my private key is going to be again encrypted, then somebody is going to ask you, where is that key for that? You have to store it somewhere. If you don't store that, you can't decrypt it, right? You can't keep on saying, passing the buck to somebody else. You store it for me safely. Finally, you have to stop the recursion or bootstrap problem and say, I am going to store it using I am not going to use cryptography and those kind of methods. I am going to use it some other methods. It has to be physical separation mechanisms, access control, or I write it in a piece of paper and I only can see it, nobody else can see it. I keep it in a pocket and I ensure I got it all times, nobody can look at my pocket, or I keep my pants somewhere, I want to make sure nobody can touch my pants when I am taking a bath also. I have to do all those things. Again, finally, what is it? It's a basically physical separation. You can't keep saying security, you can't keep saying cryptography, because the minute you say cryptography, somebody has to tell me how to manage the keys, okay. There are new techniques people are coming up with cryptography called identity based encryption, but even then it has not yet become completely well established. There may be some methods, okay. It looks a bit difficult right now to believe that will happen, but anyway, okay? People are doing some research on that, okay. But what I am trying to suggest is that you need security for some aspects of data that you use, okay, and it is somewhat different from network security. Let us see why it is different from network. Network security is across space, that is, you are sending it from one place and goes to another place, okay. So, and it happens fairly quickly. For example, you want to talk to somebody securely, you lift the phone, use a secure channel, you tell the other person something, okay, some secret, right. It happens within a short period of time, and so the piece of information that has to be protected is only for a short period of time, typically within seconds, sometimes at the most a few minutes, etc., not more than that. I am sending a packet from here to, sending a mail from here to some other place in US also, the packets will take typically few seconds, sometimes hours, in very bad situations probably a day also, sometimes it happens, okay, but usually not beyond. But what is important is that during this 1 day or 1 minute or whatever it is, my protocols don't change, my machines don't change that much, none of those things happen. Whereas if you look at the previous problem, if I do it across 100 years, everything might have changed. That also is some sense a type of data transfer. I am sitting here in 2013, I want my data to go to somebody in 2113. That was some kind of transfer. But during this period, all kinds of things could have changed. Okay, the language could have changed, right? For example, about 200 years ago, many people in India knew Sanskrit reasonably well, many educated people. Nowadays, hardly anybody knows Sanskrit, right? So if you write in Sanskrit that time, nobody is going to understand what's going on, right? Educated people, I'm talking only educated people, okay? So same thing about any language for that matter, okay? Old Latin, old Greek, they can't, the current people, the modern Greek people can't understand old Greek, for example. They can figure out a bit, but not much, okay? Old Telugu, new Telugu, all those things, language changes, the protocols change, the machines changes, operating systems, everything changes, okay? The encoding changes, all those things changes, okay? So that's why you'll find that this, since the security is across, not across space in the case of storage, it's actually across both time and space, okay? It's both across, okay? There are a lot of issues that have to be taken into account, and keys have to survive also multiple years. You can't just like that say that the key is new, okay? You have to find a way in which the keys also survive. If your keys are not available, then you can't read it, and that has already happened to many secret documents, right? Many secret documents have been encoded, and the keys have been lost, and nobody can decode it, okay? Any example of a well-known example of undecoded systems? There are many of them, okay? If you look at what is called Indus Valley Civilization, right? They have written something, but none of us are able to figure out what it is, okay? They've written it very well. I can see it's something like in physics, right? You can see the bit patterns. The patterns are visible, but I can't understand what it is, okay? So in storage systems, you have a very complicated problem because the keys also have to travel a long time, okay? So both the auxiliary information like sector sizes, etc., metadata, and keys, there also is some kind of metadata about the file, they are also transferred. Okay? If you don't have these two things, it's not possible, okay? Okay, I think we'll look at the next issues, and then probably at this point, at the end of this, I think we'll probably stop today, okay? But we'll see. So what are the issues out here? If you look at a storage system, there are two issues that important ones. What is called naming and storing. It looks very obvious, but there are a lot of deep things here also. What is the aspect of naming? Give a name to an object. Okay. This looks very trivial, right? So there is a piece of information, you give it a file name, right? File name, file contents, okay? So if you give a name to it, it might involve some processing, because you're putting it in a directory. That means somebody has to put one more additional entry into the directory, right? You have to increment the number of files that are there in the directory. Somebody has to do some processing, minor processing, but you have to do some processing. Sometimes your directories the number of files can be huge, especially if you look at your mail files. If you use something called mail dir format, mail dir, okay, mail dir format, it saves every single file or every email of yours as a single file. Now, I personally know that I have about 17,000 pieces of mail as of now, okay, since about 2002, I think, okay. I have 17,000 pieces of mail that they're sitting in my directory. So there are 17,000 files in that one directory. How many? 17,000 in one directory. Suppose I'm going to search something. So if I'm searching something, what should happen? I'm going to search 17,000 items, okay. So I can use fast techniques fine, okay. So if I want to use fast techniques, typically I need to do some possibly hashing or some index I have to keep, right? I have to keep indexes. Then only I can look at it. I could use, for example, a B tree, but then I have to, if I add a file, I have to change the B tree, okay. That means that just because I gave a name to an object, okay, does not mean that it's a very simple operation. It can mean that I need to do additional processing, okay. In addition, I can give a name through its contents. For example, somebody has a file, okay, which is, let's say, 257 bytes. I just can do a hash of the whole thing, okay. There are various types of hashing possible, and I can compute a hash on the 257 bytes. I get what is called a summary based on that hash, and I can use that as an index. If you use a good hash, it turns out that they have good what is called anti-collision properties. What does it mean? It means that given any document, it's extremely difficult to find another document which has the same hash. Okay, there's something called strongly collision resistant. Okay, that means somebody has to really work very hard. They have to solve some extremely hard problem, so that I can get another hash, another document which is the same hash, another document is the same hash. That means that if I use the right hashing model, I have a distinct name for every file. All I have to do is hash it. So some people use this also. So this is another method. Okay, and this is very useful in some situations. We will talk about it later where it's used. Okay, so one is giving a name. I told you it requires some processing. Storing an object. Okay, and storing an object also may not be that simple. May involve other reads and stores. Why should storing an object require a read? It's possible in some situations. Basically because, I'll give you an example. Suppose this is a unit of access, and a disk, for example, it can be 512 bytes. Okay, I want to write only 64 bytes, this part. Okay, but for me to given the interface to the disk, I have to first read this 512 bytes into memory, put into memory, and then update the 64 bytes, because memory allows me to write it in units of word size. Okay, I can write it in, for example, so many. I can update this part first, followed by this, etc. I update it. Once I have everything in memory, then I can put it back into disk again. So I get in from disk 512 bytes, then update it. This is basically what's called a read modify write cycle. Read modify write cycle. Okay, so even for writing, sometimes I need to do reading, and this is becoming very common in the case of solid state disk, etc. Nowadays you'll find that most of these systems also require this kind of read modify write cycles. Okay, so again, it may not be that simple also, because it can, even this can involve significant computation, because I want to write something, I may want to compress it. I have compressed file systems which can have. So I might compress it, I might have what is called secure file systems, I might have to encrypt it, I can do coding, or I can even do what is called deduplication. What is deduplication? I am writing something and it has some connection with other files which I have. There is some sharing that's going on. Okay. For example, suppose somebody is updating the states of this country. Number of states in the country is has been changing the last 1 or 2, 3 decades, right? So I have a new version of the states of the country, right? So it has got some relationship with what was there in 1960s. So there is some kind of it is similar, but there is some difference. So it may be possible for me to write the newest information as a delta of the previous information. Okay. So when I am writing it, I will see if the data I am writing it, is it similar to any other data that I already have? Can I write it as a delta of the previous information? Okay. That will essentially remove the redundancy. Okay. That means it's may not be a trivial operation, because now I have to find out, I am writing this piece of information, I have to check against all the stored objects, not one. I might have million objects in my system, I might have billion objects also. I have to go and search all these things if there is any similarity between the object I am storing and what already exists. Okay. And then if it exists, then I tell myself, okay, I will go to do a delta of the difference, and then I only store the difference and keep a pointer to the original information. That also I can do. Okay. So, but this turns out that this is computationally can be quite expensive, but this is being done. Actually, deduplication is now quite common. If you see current storage systems, they do deduplication because it reduces lot of duplicates in the system. And I think some of you might have noticed it already, basically because suppose I send a mail, right? I am attaching some file, right? So the file exists in my directory, I attach the file and send it. normally when I send my mail, I keep a copy of the mail I sent, right? That means even the attached file is also be stored as part of the mail that has been sent out. So there is a copy of the original document in a file system plus the same copy in my sent mail also. Okay. Now, people have found that as much as 80% or close to that is duplicate. So, we are talking about 100 petabytes and somebody can tell you that 80 petabytes is duplicate, right? People will say what a waste to put 100 petabytes. Okay. I will work with 10 petabytes. Okay. That is all I need, because the cost of this 100 petabytes is substantial, it is huge. Okay. It is both in terms of space, in terms of energy also. Okay. It is a huge, you are talking about 10 times your energy consumption. Okay. And you know that keeping computer systems running is a costly business in terms of energy. Okay. You are talking about 10 times energy consumption, of course for storage systems 10 times. So, I think we will continue from here next time. Okay. I come up to this point. I think basically I just was giving you some high level ideas about storage systems, why they are interesting in their own right, why they have become separated from processing. Okay. So, we will continue from here about starting with metadata versus data, etc. We will continue from here next time. Okay. Thank you.